Hello everyone, welcome to the channel. In this video, I am starting with a new topic, that is AC circuits, where AC stands for alternating current. The AC quantities actually vary their magnitude alternatively. So we can have an alternating current or we can have alternating voltage and similarly power as well. So this will be a complete series on AC circuits. In this first video, I will start with the fundamentals of AC circuits, then discuss the formulas related to AC series circuit, and in addition to that, I will also show you that how the use of complex mode of calculator is helpful in solving the problems related to AC circuits. Now, first thing which we need to understand in AC circuits, that the current or voltage, they actually vary alternatively. The current is given as Im sin omega t and voltage is known as Vm sin omega t, and they are represented by a waveform which actually varies like this, the sinusoidal waveform. It has maximum amplitude. If this is the representation of current I, then this is Im, and on this side we have omega t. It starts from 0, maximum at pi by 2 pi, then it will have negative maximum value at 3 pi by 2, and this is 2 pi. After that it starts repeating itself. So they are shown with the help of waveform, which is actually a graph in from which we can calculate the value of current or voltage at any instant. Like we can calculate the value of current at this instant. So these waveforms actually represent the instantaneous values. The instantaneous values, they are always denoted by small letters like small I, small v. Small I, small v, they are the representation of instantaneous quantities. So in this waveform, from here to here, we can say this is one complete cycle where the waveform takes all positive values as well as all negative values. So it is termed as a cycle. And the number of cycles per second are known as frequency. We have another term in case of AC, that is known as time period. And what is this time period? It is the time taken by an alternating quantity to complete one cycle. So, time period T is actually 1 upon f, where f is the frequency. This is the amplitude, the maximum value. Now in case of AC, in this case what we have seen, that we have one instantaneous value, we can have the maximum value as well. Instantaneous value is different at every instant. Maximum value is there only at one instant in the positive cycle and as well as in the negative cycle. So in addition to that, we will have two more different types of uh, currents or voltages in case of AC circuits, that is average value. It can be of voltage or it can be of current, or we can have the RMS value. It is defined as the equivalent to the DC, which would send the same amount of charge through the same circuit in the same time. Now, if you look in this waveform, the positive and negative half cycle both are same, If we calculate the average value over the complete cycle, then it will result in zero value. So when we have the waveforms looking like this, that is a symmetrical waveform, then the average value is calculated over the half cycle. So if we have a symmetrical waveform like this, then average value is calculated over half cycle. We will calculate up to here. So if this is time period T2, this one is T1, then I average is actually 1 upon T2 minus T1, that is the time span, T1 to T2 IT into dt. Now this can be even d omega t if time is varying with respect to omega t. If it is varying only with respect to time, then it will be over here dt only. Also, if we have any unsymmetrical waveform like for example the output of half wave rectifier, which is like this, then it's unsymmetrical, positive half is different, negative half is different. For unsymmetrical waveforms, the average value is calculated over the complete cycle. In next video, I will find out the average and average value of different waveforms. The next value is RMS value. The full form for RMS is root mean square value. Now this root mean square value means, how we define it? It is actually the equivalent of DC which would produce same amount of heat when when flowing through same resistance for same time. So basically we calculate it from I square into T, not dt, into T, same amount of current equivalent to DC which will flow through same resistance for same amount of time. So the RMS value, it can be calculated over the half cycle or it can be calculated over the complete cycle. But again, for symmetrical waveforms, we will calculate it over the half cycle, and for unsymmetrical waveforms, we will calculate it over the complete cycle. And how we calculate? The RMS is actually denoted by simple I or only V. Only I or only V. I average, we will write IA. V for maximum, we write IM or I max. But for RMS, we simply write V or I. And the rating of AC circuits is actually in RMS quantities only. They are used to express the rating of AC circuits. So if it is given that we have a 230 volt AC source, then that 230 is the value of RMS value of voltage. And if we said that an AC circuit withdraws 5 ampere current, that means 5 ampere is the RMS value of current. They are denoted by VE or I. It is calculated 1 by root T1 to T2 integration from T1 to T2 IT square into dt. So this is how we calculate the RMS value. Now the RM for sinusoidal waveform, IRMS is actually I max by root 2 and I average is 2 Im by pi. Similarly, we can write same for voltage. Voltage is Vm by root 2 and V average is 2 Vm by pi. So based on this RMS and average value, I will solve the problems related to different waveforms in the next video. Then in case of AC circuits, what we have seen that we have a waveform. Instead of representing these with waveform, they are usually represented with the help of phasors. Now in case of phasors, when we talk about any AC circuit, we have to draw the phasor diagram. In case of series circuits, since current is common to all circuit element, then it is considered as reference. So it is considered as reference. While in case of parallel circuits, voltage across each element is same. That's why it is considered as reference for phasors. Now in case of series, we can have the combination of resistance and inductance, we can have the combination of resistance and capacitance, RLC, or we can have even L and C. So you have to draw the phasor for each one. For every series circuit, the current is common and that is considered as reference. Similarly, we can have the parallel combination of resistance and inductance, we can have parallel combination of resistance, inductance and capacitance, or we can have even the combination of series branches like one RL and second branch is RC series branch and they are connected in parallel. So in all of them we have to consider voltage as reference. So in the coming videos I will also solve the problems of series and parallel circuits. Now before moving on to the numerical part, we need to understand one operator which is known as J operator. Now what is this J operator? J operator is actually a vector, and if we multiply any phasor with this vector j, then it will rotate that vector. Let's say we have a vector AB. Now we are multiplying this AB with j, which is a vector, then it will rotate this AB in anti-clockwise direction by 90 degree and the magnitude will remain same. So this will become JAB. If we further multiply it with j, it will rotate it further by 90 degree in anti-clockwise direction. So this will become j square AB. Now AB and j square AB, they are at 180 degree to each other, their magnitude is same. So we can write this as minus of AB. So what we get from here, that j square is actually minus 1, which is same as iota. Further multiplication will lead to minus JAB, which is just opposite to this JAB, and even we multiplication with J will bring this phasor AB to its initial position. So J raised to power 4 is actually 1. So we can say what this J is. J is actually a vector of magnitude 1 and angle is actually 90 degree because it rotates the vector by 90 degree in anti-clockwise direction. So anti-clockwise direction is taken as a conventional direction. So the angle is plus 90. So if we rotate this by 90 degree, it means this JAB is ahead of AB by 90 degree. So that's why plus 90. Now this J operator is added in case of purely inductive circuit. Let's say we have a purely inductive circuit. When we have purely inductive circuit, an inductor L across which applied voltage is V, current through this is I. We find out its magnitude that I is equal to V by XL. If voltage is over, current is over here, then voltage leads this by 90 degree. Or what we say that current lags behind the voltage by 90 degree. So if we, this is just about the magnitude. This expression is just about the magnitude. Now if we have to incorporate this 90 degree phase difference in this expression, we can write this voltage is at 0 degree, current is having magnitude, and this is at minus 90 degree because current is lagging behind the voltage by 90 degree. So when I write all these values over here, then I is at minus 90, voltage V angle 0, and in denominator we have XL. Now on both sides if we compare, on this side we have minus 90 degree angle, here we have 0 degree angle. From where this 90 degree got introduced? That is actually introduced by considering XL angle 90 degree. Now and this will be the magnitude now. So what we say that the inductive reactance is written as its magnitude and angle is 90 degree. So in case of this polar coordinates, the magnitudes they will get divided V by XL. This will give us the magnitude of current, and the angle in denominator will get subtracted from what's the angle in the numerator. So minus 90 minus 90, that's how it get balanced. So this XL is actually written as JXL. Why? Because J is one angle 90 degree. Similarly, in case of purely capacitive circuit, where current leads a voltage by 90 degree and current magnitude which is V upon XC, this is how we calculate the magnitude. Now if we incorporate the phase angles, then V is magnitude of V angle 0, current is its magnitude, and angle is plus 90. I angle 90 degree equal to V angle 0 upon XC. So how this 90 degree appears in this? Because this is there with XC as minus 90. So V XC 0 minus 90. So 0 plus 90 because this angle will get subtracted. So minus minus plus plus 90. Now angles are same on both sides. So what we say that XC is actually its magnitude and angle minus 90. We write it as minus XC. Instead of writing XC only, we write it as minus JXC. So in case of RL series circuit, where impedance is R square plus XL square under root, that is actually written in this form, in complex form as R plus JXL. Now if we just compare this, magnitude is R square plus XL square. This expression doesn't tell anything about the angle, but in this case we can actually see that how much phase difference is there. We can change this into Z angle theta form with the help of calculator. Here you calculate the theta as tan inverse XL by R. So same can be done over here. In case of RC series circuit, Z is written as R minus JXC. In case of RLC series circuits, Z is actually written as R plus J XL minus XC. So once we write the impedance, now irrespective of whether it's RL circuit or RC circuit, current is actually V upon Z, and we will get the value of this current in the form of I angle plus minus theta. So when we get the value, now depending upon the different values of resistance, inductance and capacitance, we will have the value of angle theta as positive or negative. So when the theta is coming as positive, it means current is leading the voltage, and theta is coming as negative, it means current is lagging behind the voltage. Though we say that in case of series circuits, we take the current as reference, but usually in the numerical problems, we are actually given with the voltage, and that is only about magnitude, that 230 volt source. So when we say 230 volt source, that 230 means that is only magnitude, and we consider that this voltage is at angle 0, and then we get the angles with the different with the current. So if that angle is coming as positive, it means current is leading the voltage. If that angle is coming as negative, it means current is lagging the voltage. And correspondingly, we will have the value of power factor as leading power factor or lagging power factor. Also, in case of series circuits, we know that active power is given as VI cos theta. Reactive power, which is denoted by Q, is given as VI sin theta. Apparent power, which is also known as complex power, P plus JQ, is actually V into I. So active power has units of watts, reactive power has units of volt ampere reactive, while this apparent power has units of volt amperes. So there are three different powers, and correspondingly we have the power triangle P, Q and S. This is phi, where phi is the phase difference between voltage and current. We can even draw the phasor for RL series circuit. For RL series circuits, what we have, current is considered as reference, voltage across the resistance is in same phase with the current, voltage across the inductor leads the current by 90 degree, and their resultant is actually supply voltage V, and this one is angle phi. So here current lags behind the voltage, so power factor is lagging power factor. Now in case of RC series circuit, again current is considered as reference, voltage across the resistance is in same phase, voltage across the capacitor lags behind the volt current by 90 degree, Their resultant is actually supply voltage. This is angle phi. Now current leads the voltage. So power factor is leading power factor. And in case of RLC series circuit, if we draw the phasor diagram, current is reference, voltage across the resistance is in same phase, voltage across the inductor leads the current by 90 degree, across the capacitor lags behind the current by 90 degree. Now VL and VC, they are at 180 degree to each other. Now depending upon if VL is more or VC is more, we will have the resultant. In this case, it's clearly visible that VL is more than VC, so their resultant is in same phase with VL, and then we get the resultant supply voltage of VR and VL minus VC as V, and this is angle phi. Now voltage is leading the current, or current is lagging behind the voltage, so power factor is lagging. So in this case, so instead of writing theta, we can write phi over here. So phi is actually negative. Second case is when VC is more than VL. We have VC over here and VL over here, and VC is more than VL. So the resultant is in same phase with VC, that is VC minus VL. This is VC, this one is VL, VR. The resultant of VC minus VL and VR is actually supply voltage V, which is at angle phi. Now current is leading the voltage, so power factor is leading power factor in case of RLC series circuit. So plus sign over here. So now how to solve these problems? It's always better to solve them with the help of calculator using the complex mode. Now how to use the complex mode? Let's say I have voltage given as 230 angle 0. The impedance is, and there is a circuit where resistance is 10 ohm and inductive reactance is 15 ohm. So Z will be written as R plus J XL 10 plus J 15. So now what I need to write? I need to write current as 230 by 0 upon 10 plus J 15. How can we solve this? We can solve it with the help of calculator. So I will insert a video over here that how to use the complex mode of calculator, and you will get its answer as 12.5775 12.758 and angle minus 56.309 amperes. So this means this is the magnitude of current, and this one shows the phase difference from voltage. Negative sign means current is lagging behind the voltage. Let's see how to use the calculator in complex form. For this, we need to select the complex mode of the calculator. How to select that complex mode? That varies from model to model. but usually the procedure remains same for the Casio calculators. I'm showing over here for this 991 ES model. For this I have to select the mode from setup. Now you can see that we have different types of modes available over here, and CMPLX is available at second option, so I have to press 2. So when I press 2, now the complex mode is selected. When complex mode is selected, let's say that we have to do the same calculation, that is the 230 volt divided by 10 plus J15. So I will write 230. For angle, the angle is available over here. So I will press shift this button, then angle is displayed. Angle is 0 over here. It will be divided by 10 plus J15, 10 plus J15. Now how J15 is written? It's actually written as 15 into iota. Iota is available on this ENG button over here. So we have to press ENG, close the bracket, we will get the answer. Now answer is in R angle theta form in this calculator since it's already selected. You might come across the case when you are getting answer in the form of A plus B iota. So in that case you have to select it from the calculator that in which form you want the answer. Now how to select that? For that, press shift, then setup. From the drop down menu, go to the second set of options where CMPLX is available at third. So I'm pressing 3 over here. Now this one is asking that in which form I want the answer, whether I want the answer in A plus B iota form or R angle theta form. I had already answered in R angle theta form. I want to change it to A plus B iota, so I have to press 1. Now the answer is in the form of A plus B iota. But we want the answer in R angle theta form in all our problems. So you always set your calculator to give the answer of the complex in R angle theta form. I have once again selected that. So I'm getting the answer in R angle theta form. So this is same as what I had written over here, 12.758 and angle is minus 56.309, magnitude and angle. So this is how the use of calculator in complex mode will help you in solving the problems. In the next video, I will solve the problems on the fundamentals of AC circuits, starting with the average RMS value, and then in the coming videos, I will solve the problems of series and parallel circuits. I hope this video is helpful to you. If you consider the videos on this channel helpful, please consider subscribing the channel. Thanks for watching the video.